In this example, we will show step by step how to create the system ABC block from both a structural and a behavioral standpoint. We'll start with the system and subsystem levels, and then we will add more fidelity to create the component level structural and behavioral aspects. We'll show how item flows work, how to type proxy ports, and show compatibility. We'll then scale that out to show the send event action and accept event action and how they work in simulation. We'll show all different alternatives that you see in purple and yellow there, where you can run one configuration and then run a second configuration. We'll then scale it up so that we can run the system from a system context perspective. And then we will finally show the automatic sequence diagram generation and how synchronous and asynchronous messages can work in simulation, and we'll touch into operations. So we'll first start by creating a BDD so that we can create the structural breakdown of our system ABC. So we have our system ABC block, and then we decompose it into subsystem A, B, and C. And then on subsystem A, we will call out subsystem A component 1 and subsystem A component 2. And then we will create an internal block diagram to connect the part properties together. We're going to add some proxy ports to our block, and then we will show the proxy ports on our part property within our IBD. We'll then create connections between the proxy ports, and then we will create a signal library with several signals within it. We're then going to take the power signal and drag it from our containment tree onto the connector line between subsystem A and subsystem B. This will add the power signal as an item flow across the connection. We can use the item flow manager to view all of the different signals which are crossing in between subsystem A and subsystem B. We'll quickly rename our proxy ports just so they don't have the same exact name to avoid confusion. We're going to go back to our BDD, and we're going to create a behavioral activity diagram at our top level system ABC, and then we'll start building out this activity. The system ABC activity will be the classifying behavior to the system ABC structural block. This means that when we run the system ABC block, the system ABC activity will run as well as the behavior. We'll start decomposing system ABC main activity by creating some internal actions and then creating control flows between them. So these simple actions, from sending power to other subsystems and then receiving and loading the software, and then also in parallel receiving the power and starting a boot up process, this is going to be run in simulation, and we can see that it works as intended. Now we'll go ahead and add some vertical swim lanes or activity partitions. They will automatically populate with our subsystems A, B, and C as the pop-up shows, and we can select all three of these, and we can start adding the actions which we created to the specific swim lanes. Adding these behaviors to the structural swim lanes will create an allocation relationship. We can see that the allocation mode is set to usage. This was done intentionally so that we can have actions allocated to part properties instead of activities allocated to blocks. We'll go back to our BDD and we'll pull our activity diagram that we just created onto our BDD and show it so that we can see both the behavior and the structure at once. We'll then go add some more refinement to the activity diagram by creating a control flow between the different actions. We can rename the input and output pins as we desire. We can then go into the item flow manager and see that the power row has already been pre-populated within Cameo, and that is because we added that power signal across the connector on the IBD. Now we'll create a new item flow between subsystem A and subsystem C. When we go into the item flow manager, the icon is not available, and that is because there is no item flows between subsystem A and subsystem C. Therefore, we can create a new item flow within the behavioral diagram. Instead of creating the new item flow in the behavioral diagram, we could also go back to our structural IBD diagram and create the new item flow there. So we'll create a couple of proxy ports and then a connection between the proxy ports, and then we'll add the item flow on top of that connection. Now that the item flow has been added, we can go back to our behavioral diagram and we can see that the item flow manager icon is available, and you can see that that power signal is available now between subsystem A and subsystem C. We'll go ahead and run the system ABC block in simulation, which will then kick off the associated behavior, and we can see that it runs properly. The item flows and control flows work together, and then we'll realize that the control flows are no longer necessary, so we can remove them and then rerun the simulation and notice that it still works. The item flows will supersede the control flows as we add fidelity. Now we're going to add an interface library, and inside of that we're going to add the power interface block, and this will type the proxy ports that we have created in our BDD and IBD, and this will allow us to have the compatibility checker run within Cameo to ensure that the correct signals are going over the correct connections within our IBD. To enable the compatibility checker, we will add the flow property underneath the power interface block and then type that flow property with a signal, the power signal. We're then going to change the directionality of the flow property from in out to just out, and this will show the directionality of the flow property over the proxy port. You'll see that the lines turn red because there is a compatibility issue, so we can use the tilde to conjugate or reverse the direction of the flow over that proxy port. Note, sometimes it takes a second for Cameo to rerun the compatibility checker and to make the red line go away or show up. Now let's imagine that we got the information about the specific type of power which is going to be going over the connections. So we're going to create a signal taxonomy to ensure that our compatibility checker works while enabling us the ability to add a higher level of fidelity for our signals. We've added a generalization relationship between the 12 VDC signal and the power signal. This means that 12 VDC is a type of power, as well as 5.5 VDC is a type of power. We've set the isAbstract Boolean set to true for the power signal. This is just flagging us and telling the user that we need to specify what type of actual signal is being sent rather than the abstract concept of power. We'll now go back to the IBD and we will specify the power signal that is going in between the subsystems by changing the conveyed item within the item flow manager. The connector between subsystem A and subsystem C does not turn red, and that is because 5.5 VDC is able to go over the power interface. This is because of the signal taxonomy that we created in the previous step. We see at first that the 12 VDC signal also does not have any issues, but if we go back and remove the generalization relationship between 12 VDC and power, we see the compatibility red flag. I'll use the red X icon to help us troubleshoot the error. If I click make 12 VDC subtype of power, that will inherently add the generalization relationship between 12 VDC and power and will make the compatibility error go away. Now that I added fidelity to the structure, the IBD, I can go to the behavior, the activity, and we can show that it has been automatically updated with this specific type of power signal. Now let's imagine that we get some more information about each of the behavioral steps or actions that are going to happen within the system ABC main activity. We'll go ahead and add that detail right now. We also learned that subsystem B needs to send subsystem C a data set. So we will go ahead and model that as well with a object flow, and then we will add a new signal to our signal library and then add that signal over the object flow as an item flow. Now we'll go back to our structural IBD and we can add proxy ports and then show the dataset signal going between subsystem B and subsystem C. Our purpose for showing this is to show that it doesn't matter if you add fidelity in the behavioral first or the structural first. In the first example earlier, we added the detail and item flow to the structural and then came back and added it to the behavioral. But this time we're adding behavioral first and then going back and adding fidelity to the structural. As we change the signal dataset name to just data, we see that it propagates on both the structural IBD and the behavioral activity diagrams. We'll go ahead and run our current configuration and simulation just to show that it does run as intended. Just as we did with the power interface block where we typed the proxy ports, we will do the same with the data interface block where we will type the proxy ports connecting subsystem B and subsystem C. Just as before, we will create a flow property underneath our data interface block, and we will type that flow property with the signal data. We'll ensure that our typed proxy ports are conjugated appropriately and that the compatibility checker has no errors. We're going to create a special data packet signal and then add several properties with default values. And then we're going to type the pins within our actions with the signal data packet signal. We'll see that this first throws a compatibility issue, and that's because we don't have a generalization relationship between special data packet and data. So we will go ahead and add that. Now we'll show our special data packet and data signals within our signal taxonomy, and we'll go ahead and make the data signal an abstract signal as we did the power signal. We'll go ahead and rerun our current configuration and simulation, and we'll note the difference between the power signals and the data signals. The power signals, you'll see when the red triangle goes from subsystem A to subsystem B, you will not see the signal being called out. The 5.5 VDC is not being called out, the 12 VDC is not being called out on the screen, but when we get to the data signal, we'll see that the special data packet is actually called out on the triangle as it goes from subsystem B to subsystem C. We can hover our mouse and see all the details about this as well, and that is because we have typed the pins of our data actions and we have not typed the pins of our power actions. So the next step is to add refinement to our behavior. So right now we have one single activity called System ABC Main Activity. It is the classifying behavior of the System ABC block, the system level block. The goal will be to have 3 separate behaviors at the subsystem level. You're seeing the subsystem C classifier behavior activity being created. And this is going to help show in simulation how activities can be run in parallel. You'll see when we run simulation that system ABC main activity is simulated as well as the subsystem C classifier behavior activity. These activities can communicate with one another if modeled correctly. We're now going to update our activity from using object flows to utilizing the send signal action and accept event action. This will allow us later to be able to specify what structural pin the signal is going over when transmitting from one subsystem to another. Note, since our goal is to completely remove the system ABC main activity and replace it with 3 subsystem level activities, this send signal action and accept event action step is required. If you as a modeler are okay with still having a system level activity, you could continue on with just having the object flows. One of the primary reasons it makes sense to switch from one activity at the system level to several activities at the subsystem level would be in a use case where you want to be able to swap out one of the subsystems, and the alternative one for that subsystem has a different behavior than the alternative two of that specific subsystem. We'll show this later. Now that we've set it up, we can run it in simulation by clicking the Run button. This only runs the activity and not the structure behind it. Now when I actually send the power signal from the simulation window, it does send the power command, and then the 5.5 VDC and the 12 VDC signals get sent appropriately to the other aspects of the activity, and the activity completes. However, when I restart the simulation and say run with context, this means that when I'm running the simulation, it runs both the activity as well as the structure behind it. Now, when I send the power signal, it no longer works because the 5.5 VDC does not know what port to send the 5.5 VDC over so that subsystem B or subsystem C can receive that signal. If you look in the Variables tab in the simulation window under Subsystem A, you'll see the two events. That's the 5.5 VDC and the 12 VDC that was the send signal actions that were supposed to leave Subsystem A. However, they were not able to be sent because the port was not specified. Now we're going to select all of the items in Subsystem A and then click Refactor Extract, and then we'll go through the Extract Activity Wizard to be able to create a single activity for each swim lane, Subsystem A, B, and C. Note, it may be helpful to slow the video down to be able to show all of the different wizard settings that we have selected as we created these three activities for Subsystem A, Subsystem B, and Subsystem C. While our goal is to completely remove the System ABC main activity from running, we're going to show an intermediary step where we will have a fork and show that Subsystem A, B, and C are occurring in parallel, and we'll show that that runs in simulation appropriately. You'll note that the simulation does complete as anticipated, but there are a bunch of red highlights that are going on within the Subsystem A, B, and C activities. This can be easily solved by moving the diagram itself to the right context. Note that this issue accidentally occurred when we drug the diagram onto the swim lane. By placing it into the swim lane, it actually put the diagram itself into the System ABC main activity location within the containment tree. So we can just drag and drop it back into its correct place in the containment tree, and the red goes away. So now we'll go back to our BDD, our main structural breakdown, and we're going to change the classifying behaviors. So we're going to pull the Subsystem A behavior underneath the Subsystem A block, making it the classifying behavior of Subsystem A block. And we're going to do the same with Subsystem B and Subsystem C. Then we're going to move the System ABC behavior from under System ABC to a holding tank spot, so it is no longer the classifying behavior of System ABC. Therefore, when we run the simulation, we're going to run the behavior of Subsystem A, Subsystem B, and Subsystem C, all in parallel but separately. You'll note that we know that the system ABC main activity is not running is because we can see that the initial node, the black dot, has not been highlighted in red, and we note that the subsystems are running because the power 12 VDC and 5.5 VDC are highlighted in red. Now we can go back to the system ABC main activity and we can remove all of the behavioral elements. We can remove the border and header by going into the symbol properties of each of our subsystem activities and removing the show border and show diagram header booleans within the symbol properties. We can go ahead and resize these activities to be more presentable, and then we can run system ABC in simulation, and you can see that subsystem A, subsystem B, and subsystem C classifying behaviors all run in parallel. While each of the subsystem behaviors do run, the 5.5 VDC and the 12 VDC signals are not able to be communicated from subsystem A to subsystem B and C. The reason this didn't work is because we ran it from the block ABC, which is running the structure and behavior at the same time. Therefore, we need to specify in the next step what structural port the 5.5 VDC and 12 VDC signals needed to be transmitted over so that subsystem B and subsystem C can receive those signals. So for the 5.5 VDC, we're going to select the P1C proxy port, and for the 12 VDC, we're going to select the P1A proxy port. Now we'll go ahead and look at the data signal, and we will select the data B proxy port there. Note that we only have to specify the port for the send signal event action and not the accept event action. We'll navigate back to our system structure BDD to select the system ABC block and run it in simulation. Again, the subsystem A, subsystem B, and subsystem C activities will run in parallel, and you'll see that after we send the power command that the 5.5 VDC and the 12 VDC signals are sent over the correct proxy ports, and the entire set of activities complete as anticipated. Now that we've completed the system and subsystem levels from a structural and behavioral standpoint, we can go down to a third level, the component level, and we can start specifying the structure of the component 1 and component 2 within subsystem A and dictate how these components are going to connect to the higher level subsystem A. The intention is that we learned that component 1 is going to be the one that sends the 12 VDC signal out to subsystem B, and the component 2 is going to be sending the 5.5 VDC signal out to subsystem C. Now when we run this in simulation, our activity diagrams are not exactly representative of this third level of depth. So we need to go ahead and model at the component or third level of depth so that we can make sure that our signals 12 VDC and 5.5 VDC are starting at the component 1 and component 2 part properties instead of the subsystem A part property. So now we're going to go within our subsystem A behavior and we're going to add swim lanes. The subsystem A component 1 and the subsystem A component 2 swim lanes will become available, and now we can start adding our behavioral elements within the necessary swim lanes. You can note that the 5.5 VDC and the 12 VDC send signal actions are highlighted in orange, and this is because the port which is designated is not in the correct context. The P1 uncapitalized C proxy port is within the context of subsystem A, not within the context of subsystem A component 1. So we're going to have to go ahead and update the port in which the signals are sent over. Excuse our error, we wrongly assumed that the 12 VDC was with component 2 while it was with component 1. So now we need to switch the signals swimlanes that they reside within. 12 VDC is going to reside within component 1, while 5.5 VDC is going to reside within component 2. So we'll go back and run our system ABC block in simulation just to test the component 1 and component 2 behaviors to make sure they're behaving appropriately. When we do the simulation, we recognize that we have to send the power command 2 separate times. After doing this, the entire behavior does work as anticipated and run as intended. As we did before when we were going from the system level to the subsystem level, we're going to use the extract wizard to go from the subsystem level down to the component level. Now we're going to drag the component level diagrams into the subsystem A behavior, and then we're going to drag those component level activity diagrams within the swim lane. We're going to go ahead and remove the diagram header and the diagram border just so that it looks better, and then we will go ahead and drag and drop the diagrams from within subsystem A behavior to their respective locations so that the red highlight that you see on both diagrams are going to go away. We'll now show the behavior diagram, the activity diagram on the left, and the structural diagram, the IBD, on the right, and we will run simulation, and you can see that the component level does work as anticipated. The simulation shows the 12 VDC going from component 1 to subsystem B, and it shows the 5.5 VDC signal going from component 2 out to subsystem C. Now we're going to go ahead and create a level higher than the system ABC block. We're going to create the system context, and that will allow us to send signals from the host to the system ABC. After creating the structural BDD, we'll create the structural internal block diagram so that we can connect the host part property to the system ABC part property. So now we'll open up the system level internal block diagram, and we're going to show the proxy port on the diagram frame. We're going to connect up the proxy port at the diagram frame to the component level proxy ports, and we will show the power that is being sent from the external or the host to the specific component level part properties, component 1 and component 2. We'll add our power signals as item flows on the system level IBD as well as the system context level IBD. We're now going to create a behavior that's associated with the host block, and that is going to send the power signal over the correct proxy port to system ABC. Right now I'm going back to the system context level IBD to see the proxy port, which is titled HPAL, which needs to be called out on the behavioral send signal action. Now we'll do some reformatting and pull the behavior diagrams all together and the structural diagrams all together so that when we run simulation, we can follow what's happening. When we run simulation, our host behavior is going to wait 2 seconds and then send the power signal via the HPAL proxy port. We can see on the structural IBD that the HPAL proxy port is highlighted, and then the signal goes from the host to system ABC, and then it goes down further from the frame of the IBD down to the component level on component 1 and component 2. And then the rest of the behavior works as intended. A quick note, the host behavior doesn't complete because it says at 8 seconds, and the at is relative set to false. If we set relative to true, it will be after 8 seconds and will not have this issue where it doesn't complete. Now we'll do some restructuring of diagrams so that we can see all of our diagrams within the system structure BDD. This will allow us to rerun simulation and see that everything is working properly. The next step is to show how you can model different configurations or alternatives and run them in simulation. So for this example, we're going to say that there are several different variants or alternatives for subsystem B. We're going to create the subsystem B abstract block, which will essentially just be a placeholder, and then we will create two specific types of alternatives or configurations, alternative 1 and alternative 2. We're creating a generalization relationship from subsystem B, alternative 1, up to subsystem B abstract. This will say that subsystem B, alternative 1, is a type of subsystem B abstract. We'll do the same relationship with subsystem B, alternative 2. This will allow all of the items from subsystem B abstract to be inherited down to the specific classifiers, subsystem B, alternative 1 and 2. We're going to change the specific alternatives to new colors to add clarity, and then we're going to move the behaviors from the abstract block down to the alternative 1 and alternative 2 blocks. So then we are going to have two copies of the abstract behavior, and then we're going to go in to each of them and edit them, make them the right color, and add more fidelity. In this case, we're just changing the wait time for alternative 2. We're going to go down into our system ABC main activity, which at this point is just a way to view all of the other diagrams, and we're going to add the alternative 2 behavior, which is that yellow one, to the correct swim lane. This is again just for viewing purposes, not actually for creating the allocation relationship. And this will allow us to see all of the different alternatives at one time. So again, we're doing some reformatting. We're going to put alternative 1 and alternative 2, the structural blocks, down next to the swim lane, just for clarity purposes. We're going to run our system context block in simulation. Before we actually push the play button the second time, which will kick off the behaviors, we can go down into the variables tab within simulation and see that subsystem B alternative 1 is going to be the one that's selected and ran. And so when we push the play to run simulation, we will see just the purple behavior being run, not the yellow one. Now we'll go ahead and rerun the simulation from system context, and when we go down to subsystem B, we can right click and do remove value, and then we can double click that value slot, and then it will allow you to show the different alternatives that are available, alternative 1 and alternative 2. This time we'll select alternative 2 and run simulation, and you'll see that the yellow behavior is run this time and not the purple behavior. You'll note everything worked first try as intended, and now we'll give some help on some troubleshooting if you have some issues. If you select the subsystem B alternative 2 block, and then you go down to the element properties tab and you type in class for classifier and you look for your base classifier, you do want to have the activity subsystem B alternative 2 behavior there. If you do not have that behavior there, when you run the entire simulation, that behavior is not automatically kicked off. So if we go ahead and remove the classifying behavior underneath the subsystem B alternative 2 block, we'll see when we run simulation that it doesn't work. The 12 VDC is not highlighted in red. The subsystem B behavior is not shown as an activity underneath the sessions tab within simulation. And there is an outstanding event that you can see in the variables tab within simulation that is not resolved. We have now added the subsystem B alternative 2 behavior as the classifying behavior of the subsystem B alternative 2 block. So we're now in a working state. We're now going to show you how we can automatically create sequence diagrams. To create this automatic sequence diagram, we can right-click the system context block in simulation and do create sequence diagram. We then push the second play button, which will kick off the behaviors, and you will see your sequence diagram automatically created. We'll note that all the messages that have been created on the sequence diagram have the open-ended arrow. That means that they are asynchronous, so they are the fire and forget sort of signals, and that is how the send event action works, is it is a fire and forget. So on the next example, we'll show how to create a synchronous message, which is a solid arrowhead on your sequence diagram. To be able to create synchronous messages, we will create an operation. We'll make this operation underneath subsystem A component 1, and each operation is going to have a method or some sort of behavior which is invoked when that operation is called. So we're going to create operation 1 within the holding take, and then we are going to assign operation 1 as the method to our operation titled op1. We're going to go ahead and add parameters for the inputs and outputs of our operation. Operations are similar to coded functions in the fact that once all the inputs are provided, the function is kicked off and is completed and then returns the outputs. This operation is going to be super simple, one input, one output, both of type integer. We're now going to add a opaque behavior within the method or the operation 1 activity, and we're going to add one line of code to that opaque behavior. Our line of code in this case is going to be out equals in plus 200, so we're just adding 200 to the input integer. We're going to add input and output pins, and we're going to title the input pin in and the output pin out. By labeling the input pin in, there is a linkage under the hood that is connecting that text called in within the input pin to the in variable that is within our body and language of the opaque action. That is the same with the output. So out is going to be linked under the hood to the out pin on our opaque action. Now what we're going to do is we're going to drag our op1 operation onto our activity that is under host. This is not going to be representative of how a system would work at all. We're actually going to put it before the power, which doesn't make any sense. We're just trying to show the SysML syntax and how things work in simulation within Cameo. We can go ahead and remove that target pin on the input of op1. It's unnecessary. And then we can add an opaque action that we can add a line of code, input 1 equals 6. And we can add an output pin to that opaque action, rename it as input 1, and then connect input 1 output pin as the object flow into opt1 as the input 1, and that will send that 6 number value from the opaque action to the operation 1. We're now going to create a new opaque action and say x equals output 1, and we're going to connect the output from op1 to the newly created opaque action. Now this x value is going to be a value property that we're going to create that is attached to the host block. In simulation, when the op1 is completed and it sends the output to the newly created opaque action, the opaque action will reassign the value property x to the new value. Our last step before running simulation is to specify the port which the operation is going to go from host to then connect to the subsystem A. So we're just going to use that hpal from before, and we'll select that within the specification of our operation. When we rerun the system context in simulation, we see our op1 operation pulling in the 6 value and then going through and adding 200 to that 6 value, outputting 206, and then we are able to see X be populated with the 206 value. And then the behavior continues by sending the power command, and all of the rest of the activities occur. Now that we know that our operation worked, we can go ahead and rerun the system context block in simulation. Before we push the second play button to kick off the behaviors, we can right-click the system context block within our variables tab within a simulation window, and we can do show sequence diagram, which will automatically create the sequence diagram for us just as before. Now, when we run the simulation, we'll be able to show that the synchronous message, the closed arrowhead, has occurred when we use the operation. This is the opposite of the asynchronous message, which is produced when we are using the send event action. We'll take a few more seconds to review the sequence diagram that was automatically generated. We can look at the synchronous and asynchronous messages, as well as the X value, the value property that was updated on the host block. We can also note in the containment tree that the block system context was created because of the automatic sequence diagram generation, along with the diagram itself. We hope you enjoyed the video. Please check out some of our other videos, which will go in more depth on some of these processes and techniques. Thanks.